so yeah, she's so cool. That's such a good video in class. I like a series of I like data.
I think that'll work. Okay.
You ready?
Yep.
Okay. So our speaker today is Professor William Stein from the Math Department. We'll talk about Sage.
Right, so as indicated, I'm going to give a talk about Sage, which is a mathematical software project, which I started many years ago. So, still at an angle. Haven't quite gotten this straight. I didn't realize how much of an angle this was at. Here we are. Okay, so Sage is kind of like MATLAB or Mathematica or Maple, except it's very different. The core mission statement that I came up with to describe the project when I started it, well, I came up with this mission statement a little later, but it's to create a viable, free, open source alternative to Mathematica, Maple, and MATLAB. In 2005, when I was first starting Sage, those three systems were very dominant. They were pretty much your only option if you wanted to do, if you wanted to use a piece of math software in the context of coursework in calculus or linear algebra or something else. There was a system called Maxima, but it's very clunky, especially back then. And Octave is sort of alternative to MATLAB, but it also has its issues. In particular, it's not so close to what's available with Mathematica and Maple. So what is meant by such an alternative? And the reason I came up with this mission statement was that I started getting a lot of other people involved in developing the software, and it became, initially at least, very unclear what should go into the package that I was writing with these other people and what shouldn't. And like what sort of, basically the direction of development became extremely argumentative and unclear. And by coming up with a statement like this, you can often answer questions about what Sage should do, what should go into Sage, etc. And it helps. Even a few days ago, somebody asked, should there be, a package in Sage for doing discrete simulation? I don't even know what discrete simulation is, but I can answer his question because I can say, well, if MATLAB has a package like that, then Sage should. And that was helpful. Okay, so what I mean by a viable alternative, this statement, you can actually interpret it in a lot of ways, but what it means is that mathematically you have similar features to the features in Maple, Mathematica, and so on. So you can compute symbolic integrals. You can compute reduced row echelon forms. You can solve linear systems. You can numerically integrate. You can solve ODEs and PDEs. You can draw plots of functions, 2D functions, 3D functions. You can create networks, so vertices and edges, and then ask questions about them, like you might do in Mathematica. You can do all kinds of symbolic manipulation. Also, there should be a notebook interface. Maple and Mathematica both have really nice notebook interfaces, and so we need something similar for Sage. And there should be documentation. If you're an instructor and you want to teach a course using Sage, say a course on calculus or linear algebra, it would be really nice if there were curriculum materials available to you. If you're a student and you are taking a course and you'd like to use Sage, it would be nice if you could download off the web for free a book which shows lots of examples of how to solve problems in calculus or linear algebra or whatever using Sage. So that's the sort of things that I mean by a viable alternative to these systems. That if whatever you're doing, if you'd like to use Sage instead of using Mathematica, it's at least possible. If you make it ridiculously difficult, for example, by having, if there's very bad documentation, if functionality you need isn't there, etc., it's really not a viable alternative. But a key thing that Sage isn't, you can't just take a program that you've written in Mathematica and run it directly in Sage. We don't have a parser for the Mathematica language, for example. That makes Sage very, very different than Octave. Octave tries to more or less be a drop-in replacement for MATLAB. I know it isn't. If you're familiar with Octave versus MATLAB, you'll know that There are subtle differences between the two. But more or less, that's the approach Octave takes. Sage is nothing like that. In fact, with Sage, we try to be, in various ways, one step ahead of where the other systems are, as far as what programming language we use, and so on. Okay, in this talk, I'm going to try to accomplish two goals. One, give you a sense of the history of the Sage project, just basically 2 slides about that. And the other is to show you some examples of how Sage works, and also give you a sense of the technology involved in Sage itself. Before I go on, any questions about the goal? I mean, it's a goal anyone could come up with. A lot of people did. This one seems to have got by far the most traction in the community. And when I started this, most people told me I was crazy and I would fail miserably, but it hasn't. So, so first, a little bit of motivation that this is kind of history in the sense that this was why I wanted Sage. I wanted something like Sage rather than just being happy with the existing options. I've mentioned Magma a few times here, but I haven't said it out loud until this moment. Just because Magma has so each of the systems that are listed at the top of the page, they're commercial software, they're closed source, and they have different domains of application. Magma is aimed primarily at group theory, abstract algebra, cryptanalysis and cryptography, like public key cryptography type stuff, commutative algebra. Basically, a lot of areas that you'll see if you look at the graduate level courses that you would have at a university like this in mathematics, in pure mathematics. So that's what Magma is aimed at. And as you are probably not grad students, I won't talk much about Magma. Maple and Mathematica are aimed at more symbolic applications, though they claim to be very universal. And MATLAB is aimed very squarely at numerical and scientific work. It has an enormous amount of traction in that area. Okay, so for me, personally, I find Maple, MATLAB, and Mathematica for my own research as a number theorist, a pure mathematician, useless, but I find Magma very, very useful. And so these are mainly issues for me. But some issues are that these systems are commercial. They're extremely expensive, especially if you don't get a student discount. Once you get beyond student discounts, they start having list prices in the thousands, which is pretty bad. If you ask somebody at, for example, Microsoft Research how much they pay for each copy of MATLAB, you might be shocked at the many, many thousands of dollars they actually pay. And of course, Microsoft doesn't like buying lots of software from other people, they like selling it for lots of money. These systems are closed, which kind of really seems weird from the perspective of mathematics research. You're really used to any curiosity. I mean, you chose to do math because anything you're curious about, if you work hard enough, you can read what's going on behind the scenes. There's no secrets at all. If you just put your mind to it, you can understand why anything is true. Except when you use these programs, you type f of something. You find some function, you type f of it, and you evaluate the function, and you get a number out, like 7. And you wonder, why did it output 7? And it's like the only place in your entire world, if you're a math researcher, where you're not allowed to figure out why the damn thing outputs 7. So it's just utterly bizarre to kind of have this whole world where everything you do is completely open, and then suddenly this key piece of technology that you use, namely a piece of software like Magma, is giving you numbers out, and you have no idea where they're coming from and why they're that way. And with some of the systems, when you look at their terms of usage, they include some of the code for how they do it, because they're interpreted programs. But if you look at the code and try to figure out how they work, then you're violating their terms, especially if you then re-implement something similar. So, because you're like reverse engineering. So that's annoying. And then there's other frustration that kind of goes along with that, involving copy protection and tight control of development. Another issue is that the programming languages of those 4 systems are specially designed by those companies. And so MATLAB has its own language, Maple has its own language, Mathematica has its own language. How many people here have used any of those programs? Raise your hand if you've used any of those. Do you think that they have to have their own language? Or why couldn't they use some just standard computer, language that programmers use, like Python or something? There's no reason at all that they couldn't, except that every single one of the systems, their development started in the late 1980s, before there were really very many good options for interpreted languages like we have now. It also kind of locks you in. If you write a program using, say, Mathematica, and you want to switch to using a different system, you have to rewrite it completely. If you write a program using Python, you can just possibly swap out libraries. In Sage, by the way, the language is Python. If you want a one-sentence description of what Sage is from a technical point of view, Sage is a big library that makes math easier to do in Python. That's what it is. It's a Python library for doing math. A very, very big Python library for doing math. That's what
like
it is.
NumPy?
It includes NumPy.
Oh.
Yes. Sage is, like a picture would be, here's NumPy, and then more stuff around it, and that's Sage.
Okay.
Okay? So if you're wondering what the heck is Sage, it's like NumPy. In fact, NumPy is part of it. And many, many other things. Oops. Okay, so now to summarize, what is Sage? It is, the programming language is Python. We also use Cython, which is simply a Python compiler with type declarations. It's a language very much like Python, where you can declare data types like doubles and ints, and you get dramatic speed-ups in performance by doing so. It turns Python code into C code. It's a completely standalone project that the lead developer was one of my PhD students here. Now he works at Google full-time, but he gets to work on Cython for his 20% there. So that's what Sage, that's one of the main things to know about Sage, that it is a Python, sort of a Python library. Has anyone here ever used Python? Raise your hand if you've ever touched Python. Cool, that's like half of you. Yes or no, was it easy or hard? Okay, yes. Was it easy?
Yes.
Yes. Was it hard? No. Okay, so it's generally considered an easy language to use. It's kind of like BASIC in the sense of being easy and friendly. On the other hand, it is an absolutely massive, enormous library of functions built in and other code that people have written. Very popular that way. And it runs all over the place. The second thing that Sage is it's a distribution. So in order to use Sage, we have so many different packages that we've incorporated into Sage that if you wanted to start from scratch and try to download all of those from the appropriate websites and get the versions just right and get it to all build together, and you're a super, super elite hacker expert at building code, it's going to take you months. So we make it really easy and package the whole thing together as one single file that you can download. And if you want to build from source, you extract the file, it's a tarball, and you type make, and then you wait a while, and then you get the result. There's a build system. It's a self-contained thing. So you download, extract into a directory, type make, wait a while, look in that directory, and everything's been built. And along the way, it will build Python, it will build blah, 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 lots of other things like R will get built, NumPy will get built, SciPy will get built, etc. Here's a list of some of the packages. This is on the SageMath website, which is hosted over in Fidelford. So Atlas, BLAS, Boost, and the list bzip. We include bzip just because we want Sage to be easy to build on a lot of different computers. So something that a lot of researchers will do is take the Sage tarball, extract it on a supercomputer. They got some account on some supercomputer somewhere with who knows what random software environment. And then they type make, they wait a couple hours, they look, and there's their Sage built on that supercomputer, and then they can start running jobs. Of course, the build process is somewhat intensive, and they might want to type make test to test out that it worked. And then when they come back, they get an email from the admin saying, you shouldn't run computations on the login node. But because building Sage is pretty resource intensive. For example, Atlas, this is a neat package. It stands for Automatically Tuned Linear Algebra Software. I'll just zoom this in a little. What it does is it will build something for doing some numerical linear algebra in a certain way, test how fast it is, and then try again in another way. It basically does a kind of iterative algorithm to figure out what the best parameters are, or what really good parameters are for numerical linear algebra. So it's very, very resource intensive to build. Usually when you build Sage, this component takes as much time as everything else put together. Although in some cases there's a bunch of, like you can save the answer, what's optimal on a given computer, and then reuse that. So often it gets reused if you have a very standard computer. But there's a very long list of different packages that are all included in Sage. Many of the standard open source math software programs such as GAP, Paris, Maxima, R, the statistics program, they're all part of the Sage distribution. In fact, the GCC GNU compiler collection as part of Sage. Sometimes you extract Sage and you want to build it on, say, your Mac, and the compiler has some weird bugs in it that we know of. And so we just say, screw that, we'll use your compiler to build our own GCC compiler, then we'll build all of Sage using our own compiler. So we can ship a new version of GCC that we know will build Sage without bugs that we know about. And it can make a dramatic difference. We recently had this issue where somebody built Sage and they slightly changed something in the build, and some calculation went from being, I think, 15 seconds to 55 seconds. And we're like, what happened? And we finally nailed it down to whether or not we use the system compiler on OS X versus the compiler that we ship, which made things a lot faster. So it does. There's a lot of people involved in Sage development now, and they deal with all kinds of subtle stuff like that. But the list goes on and on and on and on. There's tons of Python libraries included, et cetera, et cetera, et cetera. There's also a lot of new code that we've written, so it's more than just a distribution of other code. It's not like just it's kind of, in a sense, kind of like a Linux distribution in that you have a bunch of packages, but you also have a customized desktop that makes everything work together smoothly with nice menus and so on. So with Sage, on the other hand, you have code that ties together these different libraries. So we have code that makes it very easy to use Maxima or R or any of these systems together in a single calculation. So we have code that makes it so if you want to call something in one system in a Python program and then combine it with something in another system, it's natural and smooth. And this code is getting more and more mature over the years. So some of it started out fairly naive, just using pseudo TTYs. That is, you simulate a text console and you send commands to the program and you see what output it gives you. It's pretty easy and generic to do that. You can whip something out like that that works pretty well in a couple of days. But then if you really want to have extremely good communication between Python and, for example, the GAP program. GAP is an interactive program for doing group theory. If you want to have really good communication between those two, you have to do something that may take a lot more work and involves substantial C programming and so on. And this sort of thing has been and is being developed for Sage all the time. And it's got better and better over the years as it's matured. So these are getting quite sophisticated. And then there's lots of new code. So this new code is mainly written by graduate students who are doing a PhD thesis in some area, and they decide they'd like to implement an algorithm related to their thesis work, which in both pure and applied math is very common these days, and surprisingly common in pure math in addition to applied math. And they'll choose Sage because we peer review the code that people include in Sage, whereas if you, say you write a big program, maybe not enormous, but it's a several thousand line program as part of a thesis or something. You want it to, in some sense, be published, but there aren't really that many options. You can hope maybe that Mathematica or MATLAB will buy it. Do any of you know anybody who's written a 1,000-line program and had MATLAB or Mathematica buy it and include it? I've never even heard of it happening, but you could hope for something like that. That would give you some credibility. Another option is with Sage, we have a clearly documented process, which is very much like submitting a journal article. It involves a back and forth between some reviewers and you. It's all done publicly. Every single step is done publicly. Everyone can see it, so you know exactly what's going on. And your code can get peer-reviewed, included with Sage, and automatically tested on dozens of platforms before every Sage release. So your code has a lifetime, or a life as a result. And so a lot of code is being written by grad students implementing new things. So there's a lot in Sage that isn't anywhere else, but is often very advanced. Much more advanced than you might find in Mathematica, because our criterion for inclusion, though we will let stuff in because it's in Mathematica, say, if there's 2 or 3 world experts that are interested in some code, that's enough to get it into Sage. We don't, we're not trying to sell Sage to a wide audience, so we don't have to set our development expectations so that we only have things that are of interest to a huge number of users. All right, so that's what Sage is. Python, lots of other stuff to tie it together, new stuff. All right, quick history. I started Sage in 2005. Now it's 2013. There have been many workshops and many things happening along the way. main thing I'll highlight about this slide is that we have these workshops called Sage Days. They last about anywhere from 3 or 4 days to a week. And at these workshops, usually what we do is just get together and code a lot on the table. The last workshop was in Madison, Wisconsin, a couple of weeks ago. It was really cold, about -8 degrees before wind chill. But we wrote, I was the oldest person by far at the workshop, which was surprising to me. But basically everyone there were grad students or young postdocs, or tons of grad students and young postdocs, a couple of undergrads who were there as well. And they wrote a lot of code for computing with p-adic overconvergent modular symbols. I don't think anyone in this room knows what that means exactly. I should know what it means because it's close to my research area. So there's lots of workshops. Let's see, there were 15 last year. I didn't go to all of them. And there's 10 already scheduled this year, but I'm sure some more will pop up. I think the next one is in Hawaii, much nicer than Madison right now, in about a week and a half or 2. So yeah, it's just under 2 weeks from now. So we're renting this house called the Plantation on the North Shore of Oahu that fits like 20 people. We're all coming together and coding on Sage for a couple of days. So we have many of these workshops. Regarding Sage at UW in the near future, I teach a course. It's one of the Math 480s. I've taught it once per year every year since 2007, and it's on Sage. So if you want to learn Sage, take this class in the spring. The prerequisites are a calculus course, linear algebra course, and any computer programming language. So if you know any language at all, I don't care what language, then you have the prerequisites. So that could be MATLAB, for example. So, and in that course, you'll learn quite a lot about Sage. So you'll do lots and lots of problems. And of course, by Sage, I mean what I mean by learning Sage, really, under the hood, is you'll learn Python really well. Plus, you'll learn how to use lots of libraries from Python, and you'll learn Python as compiled style Python, which is really important for scientific computing. If you go to conferences on scientific computing using Python, like I've done, you'll find that many, many, many talks will mention Python. Yes? I don't know, but it meets 3 times a week for 50 minutes. Same as most of the math classes. What does that imply? What? Yeah, how many credits would that be?
Probably 3.
Yeah. Okay, it is 3 credits. So there's that. Also, I'll be running a small REU on Sage this summer. So if you're interested in doing intense work on Sage for 8 weeks straight, paid for by the National Science Foundation here at UW, then you can apply for this. There is another REU run through the math department by Jim Morrow, which you may or may not have heard of. Have you heard of that? So it's on his website. What you would do is apply for that REU and then indicate you want to work with me on this. And that's how the application process works. We're just combining our applications. And the REU would in fact be somewhat combined in that you'll be able to take advantage of the social options of that REU without doing any of the activities, like without actually doing the mathematics of that REU. This summer one, I'm mainly going to focus on web-related stuff. So this is for people that are really interested in HTML5, CSS, and math. So if that is like the those 3 things, HTML5, JavaScript programming, CSS, maybe WebGL, that sort of stuff, and mathematics, writing cool code for visualizing mathematical objects and so on. If that's the sort of thing that really excites you, then you may be interested in this REU. Okay, so what I have left is a demo, which is on another page. But first I want to stop and take any questions. And then if we have time remaining, I'll show you some more examples. Since I haven't showed you any actual Sage yet. I've just given you a sense of some idea for a project. Okay, questions? Any can Sage do blah or anything like that? Where's the money come from?
What systems can you install Sage on?
Anything but Windows, basically. You can install Sage on Windows, but you have to we have a pre-made virtual machine, so you have to install that, and then you run it through the virtual machine. I think it will run in Sigma also, but it's not so well supported there.
I have
Yep.
a computer with Ubuntu on it. Is there can I download this through?
Apt-get install? No. So we make a binary that you download and then you extract and run that instead from the website. So the website for Sage is called sagemath.org, and that's where you can download Sage. There's also ways to use it through the web, which are going to increase dramatically in usability in the next month. So this is where you can get Sage. You can read about 10,000 pages about Sage here. There's a reference manual that's probably 7,000 or 8,000 pages long. There's about 200 papers and books and so on that are listed at this website that use Sage in various ways. Many of them are free. You can look at them. You can use Sage itself through your web browser. And the main project I've been working on for the last couple of months related to Sage is a new web-based way in which to run Sage. So that's actually what I'm giving this talk in. This is a new thing called Salvus, which is it's kind of like, I don't know, maybe a little bit like GitHub or something, but where you can do mathematics in your web browser. And you also have a command line prompt like this. So a full Xterm console. So you can look at files and run VI or whatever right in your web browser. This is all inside of web browser. This will go live at this website, I think in less than a month, depending on how much I work when I'm in Hawaii. So. There's also a website called sagenb.org right here. Oops. For some reason, yeah. So this is a place that you can use Sage through the web. This is something that I wrote with some students really mainly in 2006 and 2007. And it's been various heroic efforts have gone into making it work with more users at once. But unfortunately, it's extremely popular. And hence it often gets completely slammed by large numbers of people at once. And it doesn't scale very well, really. So it's not the greatest. There's also one other way to use Sage that's separate from the ones I just mentioned, which is called aleph.sagemath.org. And what this does is it gives you one single cell, so one single little text editor. You can type in Sage code and then evaluate it. That's all it does. But the sort of things you can get from the output are pretty sophisticated. You can get 2D and 3D graphics, interactive widgets, all kinds of stuff. And this site should handle a very large number of users at once. It should always be fast. And the front of the SageMath website will kind of gives you very quickly guidance to some of these other ways of using Sage. So right here you see that there's a big link, try Sage online, etc. So ultimately, I want Sage, ultimately meaning in the very near future, I want Sage to be highly usable without you having to install anything at all. You pull out your phone and start using Sage through the web. And this will happen soon. But right now, it's a lot of the packages that are in Sage, they really kind of grew up in a Unix environment, so they work well in OS X and Linux and Solaris, but they don't really work very well in Windows. And by the way, we used to have an app-gettable Sage, but the problem was we have 100 different things that go into Sage, and so this guy, Tim Abbott at MIT, he wrote something so you get Sage into Ubuntu, and it would pull in these other packages, but as those packages got updated, they would stop working correctly with Sage. And it just was really uncomfortable because very often, so we have this enormous test suite with probably 200,000 different inputs that we run, and we verify that you get the right answer. Because we're mathematicians and we want the answers to be right. And it matters a lot. Like with math, you get a number slightly wrong, and that's really, really bad. Whereas with a graphical user interface, if a pixel's off, who cares? So the test suite would just never really pass with the thing for Ubuntu. And so we removed it from there, and we switched to just distributing a tarball.
So for example, it has its own GCC compiler then? Does
Yep.
it overwrite the one in Ubuntu?
When you use, no, so Sage, when you get it, it's completely self-contained.
Oh, okay.
When you get the binary, you extract it anywhere you want. Just choose a directory, extract it, and it runs right there. It doesn't touch anything else in your computer. So, which is, I think, a friendly thing to do. It uses disk space, but it doesn't touch anything else. Okay, let me start showing you Sage. So the caveat being that this is actually the new Salvus interface I'm writing, but it's very, very similar in look and feel to the Sage notebook, which is what you'd use if you downloaded Sage right now. So what you have is these input cells. You type in code, and let me do something maybe ridiculously simple first. So you type in something that would be, well, type 2 plus 2, and you get output 4 there. So you can type a bunch of code in the cell, you hit Shift-Enter, and you see the output. And it's what it does is it takes that code, feeds it to Python, and gives you the output. There's one thing, though. It's, we slightly modified the language to be a little bit more math-friendly, in that there's a pre-parser that code goes through before it gets sent to Python. The problem with Python is there's a couple of funny things. For example, integer division is floor division in at least the Python 2x series, and this is confusing. Most mathematicians, at least, would be a little bit unnerved by that, getting 0 when you type 2 divided by 3. Another issue is that in Python, the caret symbol is not exponentiation, which may or may not bug you. In Python, you have to use 2 stars, and the caret symbol is exclusive OR. But if you use LaTeX, where the caret symbol is exponentiation, you'll find that you want to type a caret symbol a lot. And that gives you the wrong thing. So in Sage, what you get is that 2 divided by 3 plus 8 is the right thing, 26 divided by 3. What happens behind the scenes is that this function preparse is run on the input, and the carets are turned into double stars, and the integers are turned into our own special version of integers that have the right semantics. There are a couple of other things like this that are convenient. For example, you can define symbolic functions with the notation that we made up, which looks a lot like what you might find in Maple. So you can write, if you want, you can write f of x equals sine of x times tan x. This is not valid Python, but it just gets turned into something very similar that is valid Python. And you can turn the preparser off, as you saw, just by putting %Python at the top, for example. Okay, so now I'll just show you the rest of the demo. So just in case you're a elite Python hacker and you're really disturbed, that's what's going on here. So here's an example of making a symbolic function. For any expression, any symbolic expression, you can make very complicated ones. You can do show of it, and you'll get a LaTeX typeset version of that expression. Whoops. So here's a plot, which is taking a second. So here's an example of making a plot of that function. So the function sin x times tan x, and there are a whole bunch of parameters I've passed into the plot command. They're very similar to the parameters that you'd have in Mathematica, except they're lowercase with underscores. And here's what you get. And this is an SVG image, so you can zoom in, and there's no pixelation. And now to show you some calculus, we can do integrate f with respect to the variable x. And you can do pretty sophisticated integrals. And then when we say show, it typesets it. The typesetting is done using MathJax. So this is not an image. LaTeX itself, that program was never run. It's a complete implementation of the tech equation renderer done in JavaScript. So it's pretty cool. It gives you really, really nice quality. And unlike in the not so distant past, you don't have to download any special fonts to use this. It automatically downloads web fonts. So there's nothing special that you have to install to get this to look beautiful. And it looks exactly like what you're used to from tech, if you have ever used tech. That's usually what I say to. I don't know, do you guys use tech at all? No? Okay, crap. Tech is the standard math typesetting program written by Donald Knuth. Stanford. Makes really good quality, publication quality formulas. And you might want to learn it if you want to make documents that look absolutely stunningly publication quality. And I'll show you what it looks like. Let's see. So if you say LaTeX of an object, it gives you back some plain text. So there's little things like frac makes a fraction, \log makes the log, etc. And this plain text, it's like kind of like HTML for describing mathematical formulas. So kind of like that. But there are many renders for it, and it looks extremely nice. And it's also pretty easy to write by hand. So that's what that example shows. I'll just show you a couple of examples involving linear algebra. So here I've made a random 3x3 matrix. And then you can ask, so this is a basic thing in really Python that we have in Sage, which is you can take any object that you've created and you can wonder, what do I do with it? These objects are Python classes. And in Python, it's easy to see what the methods are of a class and attributes. So if you do tab in Sage, then it gives you a list of all the functions that you can call on that matrix. And it's a pretty long list. So you can do things like ask for Cholesky decomposition, ask for the characteristic polynomial, compute the decomposition, Gram-Schmidt orthogonalization, Hadamard bounds, all kinds of stuff that comes up in linear algebra. Ask for the determinant, compute the adjoint. So for example, if I click here on characteristic polynomial, and then I put parentheses afterwards and hit Shift-Enter, I get the characteristic polynomial out. And if I wanted to see a typeset, I just put show in front. But the thing that makes Sage something that a lot of people really get excited about is that if that matrix, instead of being 3x3, were pretty big, the output would still appear pretty quickly. And in fact, it does much better speed-wise than many, many other programs. It has serious asymptotically fast algorithms for solving these sorts of problems. It's not just, we have functions that look good, but when you try them on real large inputs, they fall on their face. They're very sophisticated. So there's computing the inverse, solving a system, etc. And just to illustrate a little bit of the size, let's make a random 200 by 200 matrix, and then compute its determinant. That is just the first row of the matrix. It's 200 numbers in a list. That's just the first row. And then we could say %time and compute the determinant. And you can see it took about a second. So that's pretty fast for computing a determinant. Notice the determinant, the answer is very, very big. And the algorithm it uses behind the scenes for that is pretty sophisticated. Here's what it does. It has this big matrix of integer entries, and it wants the determinant. It definitely does not do expansion by cofactors, because that would take 200 factorial steps. So what it does is really weird. It says, okay, I want to know the determinant, so here's what I'll do. I will take my matrix A, I'll just take some random vector V, random, and solve AX equal to V. And then I'll look at the solution vector X, and it'll think, Cramer's rule says that if I were to write down a formula for the solution vector, the denominators in that formula would be the determinant, which is what I'm after. So it literally just looks at the denominator in that vector, and the denominator is almost the determinant. Basically, the determinant divided by that denominator is a small integer, which you can then find via some other method. And then you can ask, okay, well, how does it find a solution to AX equal to V quickly? What it does is it says, I want to solve AX equal to V. I'll just reduce everything modulo some prime number P and solve it there. And there, it's pretty amazing what it does there. But let's just say you can solve mod P very quickly. Well, that gives you the answer mod P, this vector. And then you solve a different system mod P, and you keep iterating this, and you get mod P squared, mod P cubed, and at some point it stabilizes, and you've got the answer. And then you just look at the denominator of the result. And then, of course, you wonder, how can you solve a system mod P quickly? Well, it turns out that you can rephrase the question of solving a system in terms of matrix multiplication. And then you wonder, I wonder how can I multiply matrices mod P quickly? And what you can do is you encode them as matrices with floating point entries and that are smaller, and you multiply those matrices, ensuring that there's no overflow. So you turn a big matrix multiply problem into a bunch of smaller ones using floating point numbers. And then you're at the bottom and you're like, oh, luckily applied people really like, and like video game people or whatever, they really like doing arithmetic with floating point matrices. And hence that's really, really fast in practice. And so that means that multiplying matrices mod p is fast in practice, which means solving the system's fast in practice, which means you can compute determinants quickly. So there's a lot that goes into that one line. And then, by the way, solving is not so bad, so just like a half second right there. And by the way, if we take that b, the solution, and look at the denominator, it's not the determinant, but it should be very close by Cramer's rule. See? The denominator of our random solution is just a half the determinant. So it's a pretty cool algorithm. All right, I'll show you two more quick examples. So this illustrates image compression using singular value decomposition. Well, I don't see anything happening, which is disturbing. Let me try re-entering this. Huh. Oh, I know what I did. Sorry, I've messed this up somehow. I don't know why. Oh, I guess it was working fine. I was just impatient. Typical. Sorry, it's just it's an illustration of image compression, and I'm kind of messing it up, but I'll just try it in a new worksheet. Well, while that may or may not work, oh, if that makes sense, because it's in that directory. Sorry. All right, I'll just hit enter and see if anything comes up here. Well, let me show you another example in case that one doesn't work. Just want to show, oh, here it is actually. I'm just being really impatient. Maybe my computer's sort of loaded. So here's a picture on the right and the left. What the code above does is it turns that picture, it reads the picture, which is an image called ramp.png. It reads it using PyLab, which is part of NumPy, which is a standard Python library. It reads it into memory. It then turns it into a grayscale image, and then it performs a singular value decomposition on that matrix. And then one of the applications of singular value decomposition is you basically can write a matrix as a product of simpler things that involve the eigenvalues of the matrix. So you take something that's really big, all the entries of the matrix, and replace it by a lot less information. And then when you multiply it together, what you get is an approximation for the original matrix. But you can store it in way less space. This little interact, by the way, so in Sage, by the way, you define a function and then put @interact right before the function. It'll make widgets that allow you to control the inputs to the function, which is what happened here. That's where the slider came from. This one was written by a woman a couple of years ago in the Sage course. So as you drag the slider, it'll use a different number of eigenvalues for computing the compressed image. So using 293 eigenvalues, the compressed image looks a lot better than when I used 20 eigenvalues. So just so you can see it again, say I'll use 100 eigenvalues. Let's see what happens. So it's starting to look grainier. And if we go way back there to say 33 eigenvalues, it should look pretty grainy because it's using only 5% of the space that it was using otherwise. Okay. All right, with that, I will end my talk unless there are any further questions. Yes? Brooke, Miller? Yeah. Any other questions?
How much of a time commitment per week is I know CSE assignments can like take like 5 or 6 hours if you're fast.
I think less than 5 hours for most people. Because there's programming, but I think it depends a lot. Like if you're really not very good at programming, it's going to take a lot more time than if you are. If you're good at programming, it should be usually relatively straightforward. But I don't want to. It's just so hard to give a number because everybody's different. It'll be hard, but probably less hard than a typical CSE class as far as time goes. But I'll have a lot more math in it. Okay, any other questions? Yes?
So this started as a hobby and you kept coming along the way?
Basically what happened was I applied for a lot of funding from the National Science Foundation and other organizations, and some of it I got and some of it I didn't, but overall I've got quite a bit from Google and Microsoft and National Science Foundation. But it's not so far off from my academic research in number 3. A lot of the algorithms I've coded in here have been useful for papers I've written and so on. I only started this project right after I got a job offer with tenure. So when I was I was never tenure track, but I had a job before I had an offer with tenure, and then I did not start a project like this. But I suddenly felt the freedom to do something like this when I got a job offer with tenure at UC San Diego. So that made it. Tenure gives you a lot of flexibility. Any other questions? All right, done. Thanks.
So if you haven't signed the roster,
Yeah. The roster.